Hey guys, welcome to the second video in our series on Year 10 Physics. So last lesson, we looked at distance and displacement, and we kind of started introducing some of the core concepts behind physics and motion. In this lesson, we're going to look at speed and velocity, something you're probably quite familiar with, but we're going to look at it in the physics context. So I suppose one of the important things to mention at this point is that Year 10 Physics draws in a lot of maths as well. Now most of the maths in 10 Physics is still fairly simple. It's usually only dividing numbers, multiplying numbers. We end up doing squaring at some point, but that's pretty much the extent of it. But physics is very math heavy, so if you're looking at doing physics in the future, you have to be fairly good at math as well as being able to understand the science behind it. So just bear that in mind. If you can keep up with today's lesson fairly well in terms of the math, you should be fine for most of the 10 physics unit, because it'll mostly be much of the same type of rearranging and working that you'll have to do. All right, well, without further ado, let's jump into it. So, last lesson we looked at the two concepts of distance and displacement. So if we have an object starting at point A, moving to point B along that path, we can calculate its distance by finding out how long it is along that path, and its displacement by just figuring out the straight line distance. And we also talked about how displacement is a vector quantity, which means we're interested in its direction as well as its strength, while distance is just a scalar, as in we only care about the actual value of it. So speed and velocity are related concepts in very much the same way. So you probably know what speed and by extension velocity is in everyday terms. Shows how fast you're going. But what does that actually what does how fast you're going tell you? So speed, it is the rate of distance covered over time, which sounds really complicated, but it's actually fairly easy to understand. So speed is the rate of distance over time. All right? It is how far you go over how long it takes you to go that far. And so in equation form, we can write this as speed equals distance over time. Now, velocity is very nearly the same thing, and in most of the future lessons, we're not even going to distinguish between speed and velocity. Velocity is the rate of displacement over time. So pretty much the same thing, except we're using displacement instead of distance. And so here our equation becomes velocity equals displacement over time. Thing to remember is that speed is a scalar, velocity is the vector. All right, the way I like thinking about it is speed is what your speedometer on the car is telling you, while velocity is what your GPS is telling you you're traveling at. Your GPS needs to know which way you're going as well as how fast, otherwise it doesn't know where you are. But your speedometer only tells you, let me just redo that, there you go. Your speedometer only tells you how fast you're going. All right, so one of the things you need to be able to do is actually be able to calculate speeds and velocities. Now, instead of these big wordy equations, we tend to shorten both of these into the same equation form, which is v for velocity or speed, depending on what information you have, equals d for distance or displacement over t for time. So that's the version we'll use, because variables make it easier. So you don't have to write the same thing out hundreds of times. 5 symbols is much quicker to write than the whole equation. So let's look at an example. Let's say here we have a car. Here's the car. And a copper is standing over here with his camera pointing at the car. And that speed camera can tell that this car drives, let's say 200 meters from point A to point B, and it is going to take let's say 7 seconds to do that. What is the speed of that car? So to calculate the speed of that car, we're going to use the equation v equals d over t. And the distance traveled by the car is 200 meters divided by the time it takes is 7 seconds. So 200 divided by 7, that is a job for the calculator, unless you are very good and you can do that out of your head. And we're going to round that to 1 decimal place. So 28.6 meters per second. So this unit here, meters per second, is one of the preferred units for speed and velocity. In fact, it is the preferred unit. So we prefer the unit of meters per second. Of course, in real life, we often don't use meters per second. We tend to use kilometers per hour. Now, as long as you keep everything consistent within your problems, you should really be able to use either or. But in a lot of the future lessons, we're going to be assuming that velocity is in meters per second. So it's probably a good idea to just use that as your core unit. Okay. So the second thing we want to be able to do is rearrange that equation. So we have the equation velocity equals distance over time. Sometimes you're going to be told the velocity and the time or the distance, and you have to work out the other one. So you have to be able to rearrange that equation for our unknown values. So a little visual trick I like to use to find out how we calculate those different variables. Oh! How about that? Is this little triangle here. So I'm going to put V in the bottom, D up the top, T in the bottom. And that little triangle tells us how we could calculate each of the values. So to use this triangle, you cover up the thing that you don't that you're trying to find, so for example velocity, and then the rest tells you how to find that quantity. So to find velocity, we have to go distance divided by time. If we're after the distance, we need to go v and t, which is velocity times time. If you're trying to find time, we take the distance and we divide it by the velocity. So we have these rearranged versions of the rules, where d equals v times t, or t equals d over v. Now, if you're fairly comfortable with math, you could probably do those rearrangements without having to rearrange the rule right from the beginning, or you might be able to see the rearranged versions of the rule pretty quickly. But if you're not that confident with math, that little triangle trick does tend to help. So, examples. Distance, let's take a car. We'll take a car again. Here's a car. And you're going on a road trip. and during your road trip, you notice that your average speed is 70 kilometers per hour. Now, your road trip is going to take you 1.5 hours to complete. How far are you going to end up after the 1.5 hours? So how far can you actually travel? So that's a case of we want to find the distance. So distance equals, I'm just going to write down the rule, v times t. It's good practice to always write the rule first. That way you can at least get part marks, even if you just don't know what you're actually doing. All right, so d equals v times t. Now the velocity, we're told, is 70 kilometers per hour. And we're going to multiply that by the 1.5 hours. And I'm just going to write it as a decimal because that'll be easier on my calculator. Now notice that the unit for speed here is kilometers per hour. Our time is in hours. You see how the hours and hours match up? So you do have to make sure that those units match before you can do a calculation like that. All right, 70 times 1.5, that's going to be 105 kilometers. Right, in the units, the hours cancel each other out, and so we're left with kilometers as the unit for distance. Right, that's example 1. Example 2. So now we want to have one where we need to look at the time. So let's say we have Billy here. And Billy is riding on his skateboard. I pretend my pictures are good, please. Billy's skateboard, when Billy uses all of his strength, he can go at 12 meters per second. And let's say he's aiming to roll down a ramp or across the road or whatever. And let's say he's trying to go, say, let's go 42 meters. I don't think those units are going to give us a nice answer, but you know what? In real life, you don't get nice answers. All right, so our velocity is 12. Our distance is 42. What we want to know is how long will it take Billy to go that far? So we're after the time. So start by writing down the rule. And then we'll fill in what we know. So we know that the distance is 42 meters. And we know that the time is 12 meters per second. And again, making sure that we have matching units. Meters per second, meters. Both have meters in them. And 42 divided by 12 is not one that you can easily do out of your head. So we'll grab a calculator. Oh, look at that. It actually turns out to be 3.5. That wasn't too bad. That's going to get annoying really fast if my videos keep being interrupted by that bell. All right, so 3.5. 3.5 what? Well, our speed was in meters per second, and then we had a distance of meters. That means we're left with the seconds bit, so that's going to have to be 3.5 seconds. So again, be careful of those units. Make sure that they match up. So the last thing we want to very quickly talk about is how can we identify velocity on position time graphs. So this is the same position time graph we used in the previous video, where we had the armadillo, where we were tracking where it was over time. And so we didn't really use the time portion of that graph in the last video. We are going to have a look at it now. So visually, we should be able to pick out roughly what types of velocities we have. So for the first 8 seconds, the armadillo's position is 6 meters, and it stays at 6 meters. So it's actually not moving at all. So we can say that it has a 0 velocity. After 8 seconds, it's then moving forwards to 15. So up here we can say that it has a positive velocity. Positive meaning moving forwards. Then after, what's that, 16 seconds? After 16 seconds, the armadillo is moving backwards towards the beginning. So remember, position, or rather displacement and velocity, their directions matter. So the direction here will be in the negative direction. So we'll have a negative velocity. Now if you want to find out what the actual velocities are from this graph, we would use the gradient. So the gradient of that graph is the velocity. So I might just do one very quick example calculation of that, I suppose, and we'll take the hard one. So we'll look at this portion of the graph here. If you remember gradient, rise over run. So we're looking at how much does the graph rise, or how much do we go up, which is 9. And then from 8 to 16 seconds, that's a value of 8 seconds. And hopefully you'll notice that's actually kind of the same thing we've been doing. So 9 over 8, well, that's 9 meters position change divided by 8 seconds time change, distance over time. That's 1.125 meters per second. So fairly easy to calculate them, but I think most of the time you should just be able to do this visually. So as long as you can tell that a flat line means there's no velocity, an upwards line is a positive velocity, and a downwards line is a negative velocity, you should generally be pretty good. Alright, that's everything on speed and velocity. Go and try a few of the practice problems. If you get stuck, please send me an email, hit me up on @modo, send a messenger pigeon, whatever you need to do to get into contact with me, and I'm more than happy to give you a hand, show you how things are done, even give you a call if that's ultimately necessary. So I hope that video helps a little bit. I will see you in the next video.